Welcome to Maths with EJD. In this video, I'll be talking about applications of set theory. I've made, I think, up to 13 videos previously on set theory, and we've looked at different aspects. But of course, set theory is so important that we need to see how it's useful for different applications. Okay, so the first area of application I'll talk about is in computer science. Okay, set theory is all over the place in computer science. For instance, when you talk about databases, especially for those who work with SQL, you see that at some point you have to join two sets together. You have to find the union and intersection of two sets using the syntaxes, you find in SQL. So you have data. So in databases, you have sets playing prominent roles there. And of course, in algorithms, right? Algorithms relate a lot with set theory. Okay, so let's consider um the area of probability and statistics. Probability, probability and statistics. Set theory is also very useful here. Statistics. Okay, so here, when you're looking at probability, very soon I'll make a playlist on probability, definitely. So in probability, events, you can consider events as sets. So you can say that events are actually sets. So if you say the probability of an event occurring, so you want to look at the sample space and all of that. So all of that relates to sets, okay? And of course, when you talk about the rules of probability, you can actually see the connection between that and set theory. So probability rules are connected to set theory. Okay, let's okay, I guess I want this to be green now. So the aspect I'll be focusing on in this video is this last one. That is application of set theory in logic and proofs. If you want, there are sometimes you have to prove certain things, especially in pure mathematics. So set theory plays a very key role. And one of that is it helps you to make, you use set theory in making logical arguments. And of course, you can use it for, you can use it in your proof techniques, proof techniques. So in this video, I'll be focusing a lot on this last application. Of course, for probability and statistics, you can expect playlists on them in the future. And for computer science, right? I have a playlist on computing, scientific computing with Python. So you can check that out so you can see how set theory operates in some of those areas. Okay, so let's go to what we're focusing on today, which is set theory in logic and proofs. Set theory in logic and proofs. Okay. So here we are going to explore the use of set theory in logical arguments and various proof techniques involving sets. Set theory provides a fundamental language for mathematics, and understanding how to use sets in logic and proofs is crucial for rigorous mathematical reasoning. So let's start with the first one. Using set theory in, okay, let me go perfectionistic on you a bit. Okay. Using using set theory in logical arguments. So set theory forms backbone of many logical arguments. Here we can use sets to describe relationships between different mathematical objects and to formalize statements in logic. Okay, do I write that? Do I write that or do I not? Let me just do that. Okay, set theory forms the backbone. It forms the backbone of many logical arguments, many logical arguments. So here we can use sets to describe, we can use sets to describe relationships between different mathematical objects, and to formalize statements in logic, and formalize statements in logic. Okay. So let's see some examples. Example one. Basic logical statements with sets. Basic logical statements with sets. Okay, look at this statement. Look at this statement. If a number is even, then it belongs, to the set of integers. It belongs to the set of integers divisible by 2. Divisible by 2. So that is a statement. Now let's look at the set representation of that statement. The set representation. So that is, we can say let E be the set. Let E be the set of even numbers. Let E be the set of even numbers. And D2 be the set of integers divisible by 2. Divisible by 2. Okay. So the statement made above, right? The statement can be represented as E is a subset of D2, right? E is a subset of D2. That means that a set of even numbers is a subset of integers divisible by 2, something like that. So this simply means, every element of E is also an element of D2. That's what that is. Okay, let's move on to another example. Say example 2. Example 2, logical connectives with sets. Logical connectives. Logical connectives with sets. Logical connectives with sets. So again, we have a statement. A number is either even or odd. a number is either even or odd. That's the statement. Let's look at the set representation of that statement. Set representation. So we can say let E be the set. Let E be the set of even numbers, and this special O, I hope I can write it well. Something like this. And O be the set of odd numbers, Okay. The statement can be written as E union O. E union O equals set of integers, right? Because it says a number is either even or odd. So we say let E be the set of even numbers and O be the set of odd numbers. So the statement can be simply written as that the union between even numbers and odd numbers is the set of all of integers, basically. So here we say where that Z is the set of all integers, of all integers, and the union represents the logical or, in logic, right? You have the logical and the logical or and all that. Okay, so that's that as far as using set theory in logical arguments is concerned. Okay, let's look at another part, number 2. That is proof techniques involving sets. Proof techniques involving sets. So proof techniques involving sets. Okay. Several proof techniques. I remember I have a playlist on mathematical induction. So there we did a lot of proofs. Several proof techniques can be applied using set theory, including proof by contradiction, So, and proof by induction, So these are two types of proof: proof by contradiction and proof by induction. Contradiction and proof by induction. So I have a playlist on mathematical induction, which focuses on proof by induction. Okay, so let's see how this plays out in this kind of situation. Say here, proof by contradiction. Just take a common example of proof by contradiction. Okay, so proof by contradiction, involves assuming the negation of what you want, assuming the negation of what you want to prove, and showing that this assumption leads to a logical contradiction. Okay, so let's take another example. This would be example 3 in this case. So example 3, proof by contradiction. Okay, so we have a statement. It's a common one. Prove, you need to prove that the square root of 2, the square root of the square root of 2 is irrational, So that is what we need to prove. So what we go for is this. We have to, so to prove, let's say the proof using sets. Proof using sets. So here, we assume the opposite. Assume the opposite. Since we are proving by a contradiction. And that means we are saying that square root of 2 is rational. Square root of 2 is rational. If you're assuming the opposite, so that means the square root of 2 is rational. So normally we are to prove that it is irrational, but we are assuming in the opposite that it is rational. If that is the case, then we say then if it is assumed to be rational, then we say square root of 2 is actually p over q, because for a rational number is actually the ratio of 2 integers. So then root 2 equals p over q, where p and q are integers. P and q are integers with no common factors, Okay. If that is the case, we can move on and say square both sides. We can square both sides. So if you square both sides, it means you have square root of 2 all squared, and you have p over q all squared. So, and that simply implies that you have 2 equals p squared over q squared, which is in turn p squared equals 2q squared. Okay. So what's the conclusion now? So you see that p squared equals 2q squared. So you can conclusion is that p squared is even, okay? P squared is even. So, how did you come across p in the first place? Okay. So, p squared is even. So p must be even too. P must be even. So, yeah, p squared is even because, p squared is 2 times q squared. Whatever q squared is, once you multiply it by 2, then p squared is even. So for p squared to be even, it means that p itself has to be even. So p squared is even. So p must be even. So in that case, let's let p be equal to 2k. So let p be equal to 2k based on the fact that we have seen that p has to be even, right? Based on this expression. So p squared is even, so p must be even too. So then we say let p be equal to 2k. If that is the case, we can substitute. We substitute, and then for p now, p squared now will be 2k all squared equals 2q squared. Because p is 2k, so if you put p here, so we have 2k squared. And that leads to 4k squared equals 2q squared. If we divide through by 2, that means that we have 2k squared equals q squared. So if that is the case, that simply implies that q is also even. Q is also even, because if q squared is even, from here now, we can say q squared is even. If q squared is even, then q has to be even in the first place. So, and you can see this is a contradiction. to what we're expecting. Because if P and Q are even, it means they have 2 in common. So that defeats where we are coming from. So in this case, now we can now say this contradicts, because if P is even and Q is also even, then it means 2 can cancel out and it will no longer be what we started with, because we said it should be integers with no common factors. So this contradicts, this contradicts the assumption, this contradicts the assumption that P and Q have no common factors, have no common factors, no common factors, proving that root 2, then root 2 is irrational. Okay, root 2 is irrational. Okay, so that ends the proof by contradiction. So we go for proof by induction, proof by induction. So that's B, proof by induction. Of course, this is just a kind of rehash of the whole video I made on, the whole playlist I made on mathematical induction. So by induction, proof by induction is a powerful method, for proving statements, for proving statements about elements, in a well-ordered set, Typically, the set of natural numbers. So that's what we always do prove by induction, the set of natural numbers. So let's consider example 4. Example 4. Proof by induction. So we have the statement. The statement we are considering here is this: prove that the sum of the first n natural numbers, is given by S of n equals n into n plus 1 divided by 2, the sum of the first n natural numbers. Okay, so that's first. Then let's prove using set. Proof using set now. So we have, so of course you have to talk about the base case. Base case, since we are talking about natural numbers, so the base case is such that n is equal to 1. That means that S of 1 will be equal to 1 into 1 plus 1 divided by 2, which is 1 into 2 divided by 2, which is simply 1, because this cancels out. Okay, so so if you want to use so that's what the formula gives. So S of 1 is 1. So the base case holds. So the base case holds that, if you are talking about just one number, so if you add up one number, it's just 1. So, and that is correct here. So that's for the base case. So we can say, so the base case holds. Okay. The next thing is the inductive step. This is well explained in the mathematical induction playlist, so you want to check it out. So you now assume S of k is equal to k into k plus 1. That is, it holds for this. So here what you're doing is just turn every n to k basically. So assume s of k equals k into k plus 1 over 2 holds. Assume that this holds for some k greater than or equal to 1. So the next thing is show that s into k plus 1 is simply, so for every n, you have k plus 1. So it's simply the same thing as k plus 1 into k plus 1 plus 1. So basically what is happening is that you're changing every n to k. So every n to k plus 1. So this single n there becomes k plus 1 out here. Then n plus 1 is actually k plus 1 plus 1 because k plus 1 now is representing n. So if you can prove this, then you can say you have proven by mathematical induction. Okay. And of course, we know that um we know that we can simplify, right? Simplify, knowing that s of k plus 1 is simply the same thing as, so you're adding numbers, right? So it's more like you have, okay, let me really do that correct very well, because what we are saying is the sum to the nth number, right? 1, 2, 3, up to a particular n. So if we go all the way to k, plus k, and we add k plus 1 to it, so that's like we have what we had before originally, that is k into k plus 1, then add k plus 1 to it, add k plus 1 to it. Of course, all of this all over 2 already. So add k plus 1 to it. So this is over 1. And then you have the LCM. So 2 goes here, 1. That's k into k plus 1 plus 1 into, that's 2 into k plus 1 again. So you have k plus 1 factorized into k plus 2 all over 2. And, since we know that s of n is equal to n into n plus 1 over 2. So it means that at the end of the day, we want to have every n here becomes a k plus 1. So that's what we have to do. So you can see for this n, we already have k plus 1. For this n plus 1, we have k plus 2. So, we can, just to make it look exactly that, we can say k plus 1 into k plus 1 plus 1 all over 2. So you can just work that out. So you have k plus 1 into k plus 1 plus 1 like that all over 2. So, and that is exactly what we need. So we've been able to prove now that s of k plus 1 is equal to that. So we can now say that therefore the inductive step holds, inductive step holds, completing the proof by induction, completing the proof by induction. So for more clarity, check the playlist on mathematical induction. So understanding how to use set theory in logical argument and mastering proof techniques involving sets is essential for developing strong mathematical reasoning skills. So whether it's proving the properties of numbers, functions, or other mathematical objects, these tools are foundational in mathematics. So you see that set theory is really useful in our day-to-day lives, since computing is a very integral part of our lives. So you get to talk about set theory in things like databases and algorithms, and of course in probability and statistics, where sets are events, and you also apply set theory rules in set theory in formulating probability rules. And of course, we've seen explicitly how set theory is applicable in logic and proofs, talking about logical arguments and proof techniques. So that is the end of this video. If you have not subscribed to this channel, you don't want to miss out on future videos. So do well to subscribe right now. Hit the notification bell so you can get alerted each time a new video is released. And of course, you want to comment, like, and share. Comment, like, and share so other people can benefit from the knowledge being shared here. Thank you for always stopping by. See you next time. Bye.